Welcome to another question about probability. In this case, there's a little game here. There's 6 envelopes, and in those 6 envelopes are these amounts. 3 of them have $0, 2 of them have $1, 1 has $20. They mix them up. You don't know which is which. You don't know which one has the 20 in it. And it costs $3 to play. Would you play this game? Would you pay $3 to pick an envelope? And why? Pause it and think about it. So I'm guessing some of you are saying yes, there's a chance you could win $20. It only cost you 3. Chance you could win 20, go for it. I'm guessing some of you are saying, nah, there's 5 ways I can lose and 1 way I can win. I don't like to lose money, so I'm not going to play. Maybe some of you are saying, no, I don't gamble. This is too much like gambling. But setting the kind of should I gambling question aside, mathematicians ask a different question. Mathematicians ask, should you play? And why? And that's slightly different, and you might be like, well, should I play? And what they really mean is, should you play if you want to get ahead, if you want to get money? Let me imagine if I said it was $0, $0, $0, 1, 1, and 200. Should you play? I'm guessing a lot more if you would play, because it only costs you $3. And that's a pretty good increase on your investment, right? And this whole idea is what we call expected value. Expected value, there's different ways to look at it. I'm going to teach it as being the average outcome of the experiment in the ideal over the long term. A lot there, I know. So it's really the average outcome. Okay, this means ideal in the long term here. So let's pretend like we were going to play this game over the long term in the ideal. Okay? What that means is if I played this over and over and over and over again, how much money would you expect to win per game? Okay? On average, how much would you expect to win? This on average changes things. So this answer is not going to be 0, 1, or 200. It's going to be an average of how much we would expect to win. Again, this is called the expected value. This is the idea I'm talking about. Okay? Now, there's several ways of thinking about this. I think the easiest is just to say, what if I played it? These are all, I don't know if I would say they're equally likely, but there's 3 chances of getting $0, 2 chances of getting 1, and 1 chance of getting $200. So what if I did that? What if I played this game 6 times and I got all 6 envelopes? Now, likely that's not going to happen, but if we play this in the ideal over the long term, it should come out to that. Okay? Now, let's say we played, cost us $3, we won 0. Our winnings would be negative $3. Do you see that? We have to pay $3 to play. And so in each case, we're going to lose money, except the last one here. In this case, we're going to win $197. I forgot to write the -3s in here. Okay? And now, what's the average you would expect to win over those 6 times? We're going to add those all up. 197 minus 9 minus 4 is what I'm doing. $184. We played it 6 times, so the average is 184 divided by 6. And that gives us $30.67. So, should you play? Yeah, you should play. You should play this game as long as they will let you play. Okay? Because if you do, you will win $30.67 on average each time you play it. Now, guess what? Gambling, casinos, lottery tickets, guess what the average, the expected value is for those? They're all negative. They're all negative because the casinos are winning money on the average over the long term. The lottery tickets are winning money on average over the long term. The expected value is that you lose. Okay? And so this is a really helpful idea. I'm going to go back to this one. Should you play this game? Go ahead and pause it and calculate it on your own here. Hopefully you calculated it. I'm seeing it's -3 for each of these, -2, and this one's $17. When you add these up, you're going to get $4. So on the average, we played it 6 times, $4 divided by 6 times is going to give us 67 cents on the average. So should you play? Yeah, if you want to win 67 cents on average. This is the idea of expected value. And it comes up in a lot of ways, in a lot of areas. I'm going to give you, how about this game? This game doesn't play quite as well, right? If we lose $5, lose $4, and then win 15. You can see if we add these up, I get -$8. So -8 divided by 6. What is that? 1 1/3. So you tend to lose -$1.33 on average. This is a casino game. Okay? They're gonna take videos and post on Facebook when you win, but in the end, most people are gonna lose, and on the long run, everyone loses. Okay? This comes up in another area, lots of areas actually. This is the whole idea behind insurance of any place, any car, home, auto, whatever. But I know very little about farming, but imagine you're a farmer. There's good years, there's bad years. Again, I just made these numbers up, but let's just say in 5 years, you would have these earnings. You'd have $50,000 loss in a bad year, and then $100,000 gain in each of the good years. What's your expected value? Ideal value, average over the long term. Well, you're probably thinking I could just add these up. That's 1, 2, 3, 400,000 minus 50. That's 350,000. I should show my work. 100,000 plus 100,000 plus 100,000 plus 100,000 minus the 50,000 equals $350,000. But we had 5 years, so divided by 5 comes out to $70,000. So the expected value is $70,000. Now, I will warn you, if you look this up online, you're going to find a formula. And if the formula makes sense to you and works for you, go for it. I want to show you that it's the same thing. What the formula says is you take the probability of the first outcome times whatever that outcome is, plus the probability of the second outcome times whatever that outcome is, and so on until you get all of the outcomes added up. So the expected value is often written like this, E of X. So use the farming one. What's the probability that I get a bad year? Probability I get a bad year is 1 out of 5. So I take 1/5 times -$50,000 plus the probability of having a good year, 1, 2, 3, 4 out of 5, 4/5 times 100,000. And if we calculate this out, 1/5 times -50,000 plus 4/5, 100,000 turns out to be $70,000. Ends up being the same. Now, I want to show you that these really are the same, okay? And so if you go back here, when I added all of these up, another way of doing that, you could think of this as 4 times 100,000 plus 1 -50,000. Here, let me erase that. Okay, and then what did I do with that number? I took that number and I divided it by 5. And you'll see here that this is really similar to this equation. Do you see the 4/5, the 1/5? If I think of this as 4/5 and 1/5, maybe, and maybe you see this, I don't know. A little easier to see the 4/5 and the 1/5 if I break it apart and add them together. So either way, I want to show you the expected value is the same thing. So you can think of it in this way as the average outcome of the experiment and the ideal over the long term. Just think of getting each possibility and averaging them. That's one way to look at it. I did that with the farming here. Get each of them and then average them. Or you can use this formula where you take the probability times the outcome plus the probability times the outcome. And you do that for each outcome. You'll notice I didn't do all 4 years here because this 4/5 is the probability, and I included that. So that is expected value. Let me know if you have any questions.